Error correction. In the previous lectures we have discussed about the error detection mechanisms, right? So in this lecture we will be discussing about error correction mechanisms. Error correction can be handled in many ways. The two most common error correction mechanisms are retransmission and forward error correction. In error correction by retransmission, when the error is discovered by the receiver, now the receiver asks the sender to retransmit the entire data unit. So how this error correction strategy is going to work means we will be seeing this discussion in error control and flow control in the next lectures. So in this lecture our concentration is on forward error correction, which is the second type of error correction method. So in forward error correction, the receiver can use the error correcting codes which automatically corrects certain errors. The error correcting codes are more sophisticated when compared to the error detection, but the only thing is that the error correction codes require more redundant bits than error detection. Let us now understand the concept of error correction mechanism by examining the simplest case of single bit errors. If you remember, we have discussed about the parity bit concept in the previous class, where the single bit errors can be detected by the addition of redundant bit, that is a parity bit, right? So see, this is our original data unit 11101111. So even parity means we will be counting the total number of ones. So here the total number of ones are 6, which is nothing but even. So to make this as even parity, we simply add what? 0, right? So that is the reason we have added 0, which is marked in red color. So this is the even parity, that is we have added a redundant bit called 0 here as an even parity. So adding this parity bit will allow the receiver to detect whether there are any errors in the received message or not. How the receiver is going to detect whether there are errors in the received message or not, we have discussed in the previous class. So here the question is not just about detecting, right? So here our question is, what if we want to detect and also correct the single bit errors? So what will be the answer now? If you see here, this is our original information sent by the sender 111011, but the receiver received the information as 101111. So in this position, this 1 bit has been changed to 0 bit, and in this position this 0 bit has been changed to 1 bit. So to correct these errors, what the receiver will do? It simply alters the values of these bits, right? If it is 0, it will alter it to 1. If it is 1, it will alter it to 0. We may now get a doubt that how the receiver is going to know whether the error is creeping in this particular bit and in this particular bit. So this is what we have to solve now, right? So the secret of error correction lies in locating the invalid bit or invalid bits. So the receiver must be capable of locating which bit among the received bits is invalid bit or which among the bits are invalid bits in the received information, right? Let us now discuss a detailed example of correcting the single bit error in ASCII character. Let us assume that the sender is going to send a character called small w, that is a small letter w. So its ASCII representation in 7 bits representation is 111011, right? Now to detect the error, here we have to distinguish between 8 different states. That is, the first state is telling that the received information is not having any error, that is no error, or the error can be in position 1, or the error can be in position 2, position 3, and so on. The error can be in position 7. So total number of states we have to represent here is 8 number of states. So to represent 8 states, how many bits we require? So to represent 8 states, we will be taking 3 bits, right? So 0002 111. So this represents the 0th state and this represents the 7th state. So 0 to 7 means total 8 states. So we require 3 number of redundant bits, right? But now we may get a doubt that we are adding these redundancy bits to find out the error in our original data, right? But Question is, what if the error occurs in the redundant bits? Here we have taken 7 bits of data plus 3 bits of redundancy bits, total are 10 bits. We already know that 3 bits are used to find out the 8 different states, and now we need additional bits also to cover all the possible error locations, right? So now what we are going to do is to calculate the number of redundancy bits which are represented by R to correct the data bits, that is to correct m number of data bits, the length of the resulting code must be equal to m plus r, that is the total number of data bits plus r means the total number of redundant bits. That is, the sender finally transmits m plus r number of total bits as a single unit, then r must be able to indicate at least m plus r plus 1 different states. In m plus r plus 1, this one represents that there is no error, that is this one represents the state of no error, and this m plus r states indicates the location of an error in each of the m plus r positions. So finally m plus r plus 1 different states must be represented by r number of bits, and we know that r bits indicate how many number of states? 2 power r number of states. Therefore 2 power r must be greater than or equal to m plus r plus 1. So finally we will conclude that the total number of r bits required while transmitting m plus r total number of bits is 2 power r greater than or equal to m plus r plus 1. That is, the smallest value of r which satisfies this particular equation will tell us that how many number of redundant bits are required to send along with the data bits, that is m number of data bits. To make it more clear, let us see an example. Let us take the data unit bits are m equal to 7, that is Ascii representation, we have 7 bit representation. Now let us see what is the smallest value of r which satisfies the above equation if the value of m is equal to 7. So now let us go with r equal to 1 first of all. When r is equal to 1, so 2 power r means 2 power 1, which is 2, greater than or equal to, what is the value of m? 7, plus what is the value of r? 1, plus 1 in the formula. So is 2 greater than or equal to 9? No. So we cannot take the value of redundant bit equal to 1. Now let us check for r equal to 2, that is let us check whether 2 redundant bits are sufficient or not. So what is 2 power r? 2 power 2 means 4, greater than or equal to 7 plus 2 plus 1. So is 4 greater than or equal to 10? No. So that is 2 number of redundant bits are also not sufficient. So go for r equal to 3. So 2 power 3 means 2 cube, 8, greater than or equal to 7 plus 3 plus 1. Is 8 greater than or equal to 11? No. Next go for r equal to 4. What is 2 power 4? 16. 16 greater than or equal to 7 plus 4 plus 1. That is 16 greater than or equal to 12. Is 16 greater than or equal to 12? Yes. So at this particular value, that is at the value of r equal to 4, our equations has been satisfied. That is 2 power r 16 is greater than or equal to 12. So what is the now minimum or the smallest value of r which satisfies this equation? At value r is equal to 4. So this is how we choose the value of the redundant bit r. So in the next lecture we will be discussing about one of the popular techniques for error correction, which is nothing but Hamming code. Thank you.